Having discussed the basic algebra of functions, we'll introduce two important notions, domain and range. So the domain of a function is just the set of allowable inputs. So what can I put into the function without messing things up too much? So the question for the domain is often, what things mess up my function? For example, what things will lead me to divide by 0 or take the square root of a negative number? These are the things that cause restrictions in the domain. And they're usually pretty easy to observe if you understand the properties of the functions under discussion. The range, on the other hand, is the set of possible outputs for the function. And this, I think, is harder to determine. For this, you really have to understand the functions very well. It's not easy to be able to say, for example, oh, well, I know I can definitely get this output, or definitely can't get this output. You need to actually know something about the inverse function, which we'll get to later. But in general, the range, I think, is a trickier question. It's a bit of guess and check. Of course, with a graphing utility like your graphing calculator, you can sometimes just plot the function and look at what outputs you can get. So this is a kind of easy way to get around this. But it won't help you for theoretical questions about domain and range, which are emphasized on the CLEP exam. So just to give sort of a broad overview of some famous functions, we'll discuss these functions and what are their domains and ranges. So the function f of x equals x squared has domain minus infinity to infinity, which means everything, no domain restrictions. But my range is only non-negative numbers. Does that make sense? Well, is it possible to square a number and get something negative? No. So that's why the range is not everything. It's just 0, including 0 to infinity. How about square root of x? Well, this is even more restricted. I can't take the square root of a negative number. I mean, I can if I allow imaginary outputs, which in this class I don't, but you may take courses later where this is reasonable. But for us, you can't take the square root of a negative number. So the domain is restricted. No negative numbers allowed. And we see that here. The domain is 0 to infinity. So the key point is no negatives. How about for the range? Well, it's also restricted. I can't get anything negative as an output. So the range is also 0 to infinity. The logarithm has domain 0 to infinity, not including 0. And we saw this with the plot. It went close to 0, but never quite got there on the x-axis. The range, however, is everything, minus infinity to infinity. Now, what about the exponential function? Well, this has domain everything, but range only 0 to infinity. And this makes sense given the picture, right? So what's the log picture? It's like this. And what's the exponential picture? Well, it's almost like a mirror image of that in some sense. And we'll actually make very precise in what sense these pictures are related. It turns out that the logarithm is the inverse function to the exponential function. In a way we'll make precise shortly. Inverse functions have switched domain and ranges. So it's totally reasonable that the domain of the exponential function is the same as the range of the logarithm, and the domain of the logarithm is the same as the range of the exponential. So this really should not be surprising at all. Lastly, we'll look at a function that has kind of a more interesting restriction on its domain and range, the function f of x equals 1 over x. So this function looks like this. Now, I clearly have a restriction in the domain. Why? What would prevent me from allowing a certain point into the domain? Well, dividing by 0 is a big problem. And here I have 1 over x. So when x is equal to 0, I'm dividing by 0. Catastrophe. So I have to exclude that point from the range, or the domain. And for basically the same reason, 0 is also not in the range. So I'll say can't divide by 0. And that's what causes these restrictions. So what about this notation? There should be minus sign there. So I go from minus infinity to 0, and then also from 0 to infinity. So another way of saying this is everything but 0. Of course, I have the curly parentheses to indicate I don't include the endpoints, versus the square brackets to say do include. So in case anyone's unfamiliar with that, I'll write it here. So a nice way to understand domain and range is if you're given a picture, sometimes you can really understand the domain and range just from that. The domain will be all the points I'm allowed to look at. The range will be, well, what values do I achieve? So looking at this picture here, I have the function x over x squared plus 1, which is really not obvious what that looks like. But if I give you a picture, you can tell me that, well, it looks like the domain is everything. I have no issues. Admittedly, I'm only looking at x running from negative 50 to 50. But in that case, that tells the whole story. How about y values? Well, the biggest y value I get is 0.5, and the smallest one is negative 0.5. So what I have is range is equal to minus 1/2 to 1/2. Okay, so kind of nice to be able to just look at the picture and infer these things. So for the following functions, I'm going to ask you to plot them and then also understand the domain and range. So start with square root of 1 minus x. So let's make a little table of values. So if I plug in x equals 0, I'm going to get 1. 1, I get 0. And how about 2? Well, 2 would have me taking the square root of negative 1. So I'll say there's no output there. Or actually, instead of that little asterisk, let me try this. I'll just put a dash there. No outputs. How about negative 1? Well, that'll give me square root of 2. Negative 3 will give me square root of 4, so 2. So maybe I see the picture now. X is 0. Get this point. Okay, so that's my plot. So then I can say, well, what's the domain? Well, negative infinity and then up to 1. I can't go any further this way. No good. How about the range? Well, the range appears to be all non-negative numbers. So in this case, it was helpful to plot the function first, and then I was able to infer the range and domain. How about this one? Let's play the same game. We'll draw a little table. When x is equal to 0, I have 2 to the 0 plus 1, so 2. When x is 1, I get 3. Right, and then how about like minus 1? I'll get 2 to the minus 1 plus 1, so 1/2 plus 1, so 3/2. So the picture is something like this. Okay, so let's talk about the range and domain. Well, the range is the interesting one here. The smallest value I can get for, well, the domain for, the range for f of x equals 2 to the x is 0 to infinity, not including 0. So if I add 1 to it, I'm going to get everything greater than 1 but not including 1. So 1 infinity, which makes sense because I get close to 1 but never quite hit it. And then the domain is everything. There's no issues here. I can exponentiate a negative number, no problem. So one more example. Ooh, this one's killer. Negative natural log of 2x plus 1. So again, we'll just try and sketch this. So at 0, I have natural log of 1, which is 0. At x equals 1, I have negative natural log of 3, which is something like negative 1. Since natural log of e is 1, and e is close to 3. Okay, so what does this tell me? Something like this. Okay, and let's figure out when things go crazy here. So natural log normally has a problem when it's evaluated at 0. So for us, when is 2x plus 1 equal to 0? Well, that's x equals minus 1/2. So I'm going to have a big problem here. So the picture is something like this. Okay, and from this, I can sort of tell what the range and domain are. So the range will still be everything. From this, it's clear I'm going to get all positive numbers because I'm having rapid growth this way. Now here I have slow decay, but I will get everything. So I do have the full range, and then for the domain, clearly I have an issue at minus 1/2 and anything less than that, but otherwise I'm good. So here I basically had to take what I already knew about the domain and range and the picture for the natural logarithm and just incorporate these manipulations. That's adding a minus sign, putting a 2x plus 1 in there. You should become comfortable with these types of manipulations. It doesn't come overnight. It requires a lot of practice, and if you have your graphing utility available, just honestly plugging in different functions into the y equals command. This can really help you sort of get some insight into the basic shapes and the role of these small manipulations. We will look at the role of these kind of minus signs a little bit more in later modules.